Welcome to Physics Guide channel. My name is Raju. I am physics lecturer. We will continue moment of inertia. Moment of inertia of a solid cone. Let us consider a solid cone of mass m and radius of base r, height h. To find the moment of inertia of the solid cone, we need to consider one element of mass dm, and that element is in the shape of a disk. Look at this picture. This is a element whose radius is r, whose radius is small r, and which is at a distance x from the vertex of the cone, and dx thickness, and its mass is dm. To find the mass of this elemental disk, dm is equal to density of the element or density of the cone multiplied with volume of the element. Density of the cone is mass of the cone divided by its volume, 1 by 3 pi r square h, its volume, into volume of the element. Element is in the shape of a disk. So disk having a little thickness, it looks like a cylinder. The thickness is dx, and its base area is whose radius is smaller. So base area is pi r square. So therefore, volume of the element is pi r square dx. Then we will get dm. To get the dm, we need to find r, small r, radius of the element disk. To find the radius of element disk, let us consider only this part, this triangle. So I will draw this triangle here. OAB is one triangle, OCD is another triangle, and these two triangles are similar triangles. Why they are similar? This angle is common for those two triangles, and this angle and this angle are same, therefore 90 degrees. So AA criteria, these two triangles are similar. So if the two triangles are similar, their corresponding parts are proportional. We know that if the two triangles are similar, their corresponding parts are proportional. Corresponding parts are OA is corresponding to the OC. AB is corresponding to CD. So OA divided by OC and AB divided by CD are equal. Okay. Therefore, H divided by X, H is OC and X is OA. H divided by X is equal to capital R by small r. Then if we rearrange the terms, we will get small r. Small r is equal to R, capital R by H into X. So substitute this small r value in the dm equation. Then dm we will get as dm is equal to 3m by pi r square h into pi into r square by h square x square dx. Okay. So then just do some simple algebra. R square will cancel, pi will get cancelled off. This h into h square will become h cube. 3m by h cube into x square dx is dm. Moment of inertia of the disk is di is equal to 1 by 2 dm into r square. Substitute the dm value and r value in this di expression, di equation. Then di is equal to 1 by 2 3m by h cube into x square dx into r square by h square into x square. Then di is equal to 3m r square, 3m into r square, and 2h cube and h square multiplied 2 into h power 5, then x square into x square, x power 4 dx. This is di. So moment of inertia of the disk, element disk, di is equal to 3m r square by 2h power 5, x power 4 dx. If we integrate this di from 0 to h, because x is varying from 0 to h, in this cone, x we considered as distance from the vertex of the cone. So distance from the vertex of the cone, x is at 0, x is equal to 0, means the disk is at the vertex of the cone, and x is equal to h, then disk is at the bottom base of the cone. So as x changes, we will get the different disk. If we add up all those disks, we will get the entire cone. So x is varying from 0 to h. Substitute the limits, proper limits. I is equal to integral 0 to h di value is this. And then we know that 3m r square by 2h power 5 is a integration constant. Take out of the integration, and integration of x power 4 will be x power 5 by 5, and limits are 0 to h. Substitute the upper limit and then minus lower limit. After substituting upper limit, we will get h power 5 by 5 minus after substituting the lower limit, we will get 0 power 5 by 5. So this is no value, it is just a 0. So we can not consider it. Okay. Therefore, moment of inertia of the cone, solid cone is 3m r square by 2 into h power 5, h power 5 by 5, h power 5, h power 5 cancel off, 2 5 times 10, 3 mr square by 10. 3 mr square by 10 is the moment of inertia of the solid cone. And next we will discuss moment of inertia of the hollow cone. So to find the moment of inertia of the hollow cone, we need to consider again elemental mass, a small element. Here element is a ring whose thickness is dx and which is at a distance x from the vertex of the cone. Okay. Now this is a vertical width and this is an actual width. And here is an angle theta. So therefore, we will get, so from this right angle triangle, secant theta is equal to hypotenuse, that is actual width by dx. Send this dx to the left hand side, then we will get actual width. Actual width is equal to secant theta dx. Now we know how the actual width of the strip, that is a elemental ring, is secant theta dx. So as cone of mass m and radius r, height h, then we need to find its slant height. We need to find the slant height. Simply we can find the slant height by taking the right angle triangle. In this is r and this is h and this is l. So l is equal to slant height. A slant height is by using the right hand Pythagoras theorem. L is equal to root over h square plus r square we will get. So curved surface area is equal to pi rl. We know that curved surface area of the cone is pi rl. Pi r into l is root over r square plus h square. Now we will find the element mass. So element mass dm is equal to density into area of the element. So what is the density? Density is mass divided by its area. Mass divided by its area is pi rl. L is nothing but root over h square plus r square. Therefore, pi r of root over h square plus r square is the area of the cone. Now, 2 pi r secant theta dx is the area of the element. Element is in a ring form. It looks like this, a ring. Then if you cut it into and place it on the table, it looks like a rectangle whose length is 2 pi r and whose width is secant theta dx. Secant theta dx. Therefore, 2 pi r secant theta dx is the area of the element. Now, what is a small r? This small r, radius of the ring, elemental ring. So we can find the radius of the elemental ring by using this triangle. So in this triangle, this is the h, height of the cone, and r is radius of the cone. And this is slant height, root over h square plus r square. This is a theta, half angle of the cone. Now secant theta, in this right angle triangle, secant theta is equal to hypotenuse divided by adjacent side. Okay. And we substitute that secant theta value in the above equation. And also we will substitute the small r value. How to get the small r value? Again, we will take two similar triangles. Like a previous example, similar triangle of OCD is similar to triangle OAB. As they are similar, corresponding parts are proportional. H by x is equal to r by r. So small r is equal to r by h into x. Substitute this small r value and secant theta value in the dm. Then we will get the dm value. Dm is equal to m by, after substituting secant theta value, small r value in the dm, we will get m by pi r of root over h square plus r square, 2 pi into r by h into x, root over h square plus r square by h into dx. So this h square plus r square will cancel out, numerator and denominator. And pi cancel, r get cancelled out. Then what are the remaining terms? We will write m, 2m divided by h into h square into x dx are left. So this is dm value. Dm value is 2m by h square into x dx. Then the mi of the elemental ring is di is equal to dm r square. Dm is this value and r square is this value. Okay, r square by h square into x square. This is r square value. Di is equal to, after simplifying, di is equal to h square into h square, we'll get h power 4, 2m into r square, 2m r square, x into x square is x cube dx. Di is equal to this, and then we will integrate this di from 0 to h. Again, this x is varying from 0 to h only. Okay, so as I explained in the solid cone, so similarly, x is varying from 0 to h. Integral 0 to h, 2m r square by h power 4, x cube dx. This is integration constant. We can take out of the integration, and then x cube integration will be x power 4 by 4. Then substitute the limits. We will get moment of inertia of hollow cone, 2m r square by h power 4 by 4. Okay, h power 4 get cancelled, 2 mr square by 4. 2 1 table, 2 2 table. Mr square by 2 is the moment of inertia of the hollow cone and moment of inertia of the rod about an axis passing through the center of the rod and perpendicular to the plane of the rod. And first we need to consider an element which is at a distance x from the axis and whose thickness is dx, and we need to find its mass. Dm is equal to linear density of the rod, linear mass density into length of the element. Okay, so linear mass density dm is equal to total mass by total length into element of length is dx. Then we will get di is equal to dm into x square. Dm into x square is a di. So if we integrate this di, we will get the entire moment of inertia of the rod about the given axis. Now, just you substitute the m value and x square dx, dm value, sorry. And what are the integration limits? This that x is varying from minus L by 2 to L by 2. We substitute them. Here we will get the integration of minus L by 2 to L by 2. M by L x square dx is the moment of inertia of the rod. So m by L is the integration constant. Take out of the integration. Integral x square dx is x cube by 3. L by 2 minus L by 2 are the limits. Substitute the limits properly. M by L into, so if you substitute L by 2 in the place of x, then we will get L cube divided by 2 square, 8, 3 times 24. I will write again x cube divided by 3. If we substitute L by 2, so in the place of x, we will get L by 2 whole cube divided by 3. L by 2 whole cube means L cube divided by 8 into 3. L cube divided by 24 we will get. Similarly, other one also, minus L cube by 24. Then minus into minus plus, it will become 2 times of L cube by 24. 2 1 table, 2 12 table, then L 1 table and L square will be left. So ML square by 12 is rod. If axis of rotation is at one end of the rod, then the limit, lower limit is 0 and upper limit is L. So X will vary from 0 to L. That is the difference. Then integral in the same di, we have to integrate it from 0 to L. That is the difference. M by L x square dx. So m by L is taken out. Integral x square is x cube by 3. Substitute L, L cube by 3. Substitute 0, that is 0 only. We need no need to write it. And then m by L, L cube by 3. So L 1 table, L square, ml square by 3 is the moment of inertia of the rod about an axis passing through one end of the rod and perpendicular to the plane of the rod. As mass distributed is far from the axis at the end of a rod compared with the axis at the center of the rod, then moment of inertia at the end is greater than moment of inertia at center. What does it mean? Simply, this is same rod, we need to find the moment of inertia about this axis, which is passing through the end of the rod and perpendicular to the plane of the rod, and same mass, same length rod, and this is another axis. Okay, it is end, it is passing through center. So moment of inertia about this rod, so is ml square by 12. Moment of inertia about this this axis, then it is ml square by 3. Clearly, ml square by 3 is greater than ml square by 12. Mass is distributed far away from this axis, first this axis, when it is passing through end of the rod. Whereas mass is distributed same and which is less away from the axis. So that's why moment of inertia here is more, moment of inertia here is less. And the moment of about an axis perpendicular to its plane is equal to this theorem is valid for now. We will find the moment of inertia of a ring about its diameter. We know that moment of inertia of the body, moment of inertia of the ring about its axis, which is passing through the center and perpendicular to the plane of the ring. We know that. Okay. According to the perpendicular axis theorem, Iz is equal to Ix plus Iy. In this picture, clearly, Ix is equal to Iy because each and every diameter is similar. Okay, Ix and Iy, two diameters are perpendicular to each other, and they are just the diameter of the ring. Therefore, their moment of inertias are same. Let us say it is I. Iz is equal to mr square. Already we found moment of inertia of the ring about its axis is mr square. On left hand side, we will substitute mr square, and right hand side 2i. So moment of inertia of the ring about its diameter I is equal to mr square by 2. By using the perpendicular axis theorem, we get the answer. Moment of inertia of a ring about its diameter is I is equal to mr square by 2. Let us find a moment of inertia of a ring about its tangent parallel to the diameter. Tangent parallel to the diameter. By using the parallel axis theorem, we can find it. So we know now moment of inertia of the ring about its diameter is mr square by 2. So we need to find the moment of inertia of the ring about its tangent and parallel to the diameter. Therefore, this distance is r. According to the parallel axis theorem, I is equal to mr square plus mr square by 2. If we add them up, we will get 3 by 2 mr square. So moment of inertia of a ring about its tangent parallel to the diameter is I is equal to 3 by 2 mr square. We will apply moment of inertia of a ring about its tangent parallel to the axis of ring and perpendicular to the its diameter. So again, same parallel axis theorem. This we know mr square, and this is r distance away. So mr square plus mr square, we will get 2 mr square. Then the moment of inertia of the ring about a tangent which is parallel to the axis of the ring and perpendicular to the plane of the ring. That is I is equal to 2 mr square. Next question. Moment of inertia of a disk along its diameter I is equal to mr square by 4. You can find it very easily. Moment of inertia of a disk along its diameter. We know that moment of inertia of the ring of the disk about its axis is mr square by 2. About its axis is mr square by 2. We want to find the moment of inertia of the disk about its diameter, which is this is z-axis, let us say. Now this is x-axis. Okay, this is y-axis. And we need to find the moment of inertia about this x-axis or this about this y-axis. Ix, as disk is also symmetric, Ix is equal to Iy is equal to I. We need to find this I. Okay, according to the perpendicular axis theorem, Iz is equal to Ix plus Iy. So Iz is mr square by 2. Mr square by 2 is equal to Ix plus Iy. Ix and Iy are equal, and I, therefore 2I we will get. Send this 2 to the left hand side, then we will get mr square by 4 is equal to I. Moment of inertia of the disk about its diameter is mr square by 4 by using perpendicular axis theorem. This way we can apply parallel axis theorem and perpendicular axis theorem to find the moment of inertia of bodies about their general axis. Similarly, moment of inertia of a disk along the tangent parallel to the diameter I is equal to mr square by plus mr square by 4 equal to 5 mr square by 4. Simply, this is a disk. Just now we found the moment of inertia about this diameter is mr square by 4, and we need to find the moment of inertia about this parallel axis and in the plane of the disk. Okay, this parallel distance is r. Therefore, mr square by 4 plus mr square is the moment of inertia of this disk about this axis, about this tangent. And similarly, moment of inertia of the disk along the tangent parallel to the axis, parallel to the its axis. Its axis moment of inertia is mr square by 2, and which is at a distance r away from the parallel axis. Therefore, 3 by 2 mr square. Identical thin rods, each of length L and mass M, are welded perpendicular to one another as shown in below figure. The assembly is rotated about an axis that passes through the end of one rod and is parallel to the another. Determine the moment of inertia of the structure about the given axis, about this axis. Okay, here a system is given, and this is a of rod 1. This is rod 1, first rod, and this second rod, and this is third rod. These three rods are mutually perpendicular to each other. Okay, therefore let us consider first rod is along x-axis and second one along y-axis, third one along z-axis. We need to find the moment of inertia about an axis which is passing through the one end of the rod, which is passing through the first rod end and parallel to the second rod. Okay, so that is a question. We need to find this I. So to find this I, first we need to find I1, I2, and I3. Substitute and then add them up. After adding these three, we will get moment of inertia of this I. So then I1, moment of inertia of the rod along x-axis about given axis is about given axis. As this given axis is one end of the rod, already we found end of the rod moment of inertia is ml square by 3. ml square by 3. Okay, I1 is equal to ml square by 3 we got. Now we will find moment of inertia of a rod along y-axis about given axis is. See here, this rod along y-axis is parallel to the given axis. Parallel to given axis. Each and every element, if you consider a small element, which is at a distance L by 2 distance away from the axis. And if you consider here element L by 2 distance away from the rod, away from the axis. This one L by 2 distance away from the axis. This one L by 2 distance away from the axis. Therefore, moment of inertia of rod along y-axis about given axis is I2 equal to m into how much distance away from the rod? Away from the axis, L by 2 distance away from the axis. Therefore, L by 2 square, m into L by 2 square. I2 equal to ml square by 4. I2 is equal to ml square by 4. Next, moment of inertia of the rod along z-axis about a given axis. About z-axis, we need to find I3. So to find that I3, this is the rod, okay, and this is I3. Okay. Now, moment of inertia of the rod about its axis is moment of inertia of the rod about its axis is ml square by 12, and this axis is parallel to the required axis I3 axis. So parallel distance is L by 2. That perpendicular distance between these two parallel lines is L by 2. Therefore, by using parallel axis theorem, then I3 moment of inertia of the rod along z-axis about a given axis is I3. I3 is equal to m L by 2 whole square. L by 2 is a perpendicular distance between the parallel axis plus ml square by 12. Ml square by 12 is a moment of inertia of the rod about its axis. About its axis. So ml square by 4 plus ml square by 12, we will get ml square by 3. Ml square by 4 plus ml square by 12, just do LCM. 4 ml square by 12 we will get. Then 4 1 table, 4 3 table, ml square by 3. I3 is ml square by 3. Next, we will find a I. Moment of inertia of the system about the given axis is I is equal to I1 plus I2 plus I3. And I1 is ml square by 3, I2 is ml square by 4, I3 is ml square by 3. So add them up. Finally, we will get moment of inertia of the system, these three rods system about a given axis 11 by 12 ml square. And next one, very important concept in the moment of inertia is mass distribution property. What is mass distribution property? If size of a body in any or all dimensions is increased in such a way that its mass distribution about given axis of rotation remains the same, then the expression of moment of inertia also remains the same, which means, for example, if you consider this is a rod, moment of inertia of this rod about its axis is ml square by 12. We know that. Okay. If you increase number of same rods, similar kind of rods. Okay, we will get a planar lamina, rectangular planar lamina. Okay. And the moment of inertia of this rectangular planar lamina about the same axis is ml square by 12. That's what they are saying in this mass distribution property. Mass distribution property. If size of a body is increased in such a way that its mass distribution about the given axis of rotation remains the same, mass distribution is remains same, then the expression for the moment of inertia is also same. That is mass distribution property. Let us take a few examples to understand mass distribution property. Hollow cylinder derived from rings. Okay, hollow cylinder. This is a cylinder. How we will get a cylinder, hollow cylinder? This is one ring. On one ring, if you keep one more ring, and another ring if you keep, and another ring, next ring, next ring, next ring. Okay, next ring. So next ring, next ring, next ring, we will get a hollow cylinder. So hollow cylinder is derived from the rings by placing the masses distributed about the axis. Similarly, this axis, this is the axis, masses distributed similarly, same manner. There is no change in the mass distribution. Okay, similar manner mass distributed. Therefore, moment of inertia of the ring is mr square. There and moment of inertia of hollow cylinder also mr square. Solid cylinder, if we take, okay, if you keep a one coin, 5 rupee coin here, it is a disc, a disc, and on it one more coin, one more coin, one more coin, one more coin. And then finally, we will get a solid cylinder. Is it right? We will get a solid cylinder. Like this. Solid cylinder we will get. So solid cylinder is simply derived from the disk. The moment of inertia of the disk is equal to the moment of inertia of the solid cylinder because of mass distribution property. Mass is distributed equally about the axis of rotation. Therefore, moment of inertia of the body whose expression is not changing. It is similar. It is same as before. So moment of inertia of the disk is mr square by 2. Moment of inertia of the solid cylinder is also mr square by 2. Moment of inertia of the rod is ml square by 12 and a rod of a square cross section. And moment of inertia of the rectangular plate is also ml square by 12. On changing the dimensions and expression for moment of inertia will not change. Okay, let us take one more example. Mass distribution and moment of inertia. Okay, one more example. And moment of inertia of this rectangular is a rectangle about this axis, x-axis is ml square by 12, about y-axis is mb square by 12. Just expression is same only. This number is changing. B here, this is L. That is a difference. Okay. So now we want to find the moment of inertia about this z-axis. Iz is equal to, by using perpendicular axis theorem, we can get it. M by 12 into L square plus B square. Okay. So then Iz equal to M by 12 into L square plus B square. If we increase number of such rectangular laminas, we will get a box. Moment of inertia of a box derived from rectangular lamina is same as a rectangular lamina moment of inertia. Moment of inertia of the box will be Iz equal to M by 12 into L square plus B square. The figure shows a book-like object. One side is longer than the other, and 4 choices of rotation axis, all perpendicular to the face of the object. Rank the choices according to the rotational inertia. Rotational inertia is nothing but moment of inertia of the object about the axis. Greatest first. Greatest we have to give first rank, and next least we have to give the last rank. So observe this picture. The mass is distributed far away. This is a rectangular lamina. This mass is distributed far away from the first axis. Therefore, moment of inertia of this rectangular lamina about the first axis will be large. So this one giving you first, I'm giving you first rank. This is first rank, and similarly this is second rank, and then this is third rank. Fourth one is the third rank, and this is the fourth rank. Okay. So according to the mass distributed far away from axis 1, therefore moment of inertia about this axis is more. Similarly for other axis. So I1 is greater than, I2 is greater than, I4 and greater than I3. That's it.